Okay. Hello. Good morning. Good afternoon. Good evening. Welcome to AI-driven networks working group. I appreciate your participation. I'm Professor Wang Chul-song, working for Jeju National University, Korea. I'm also one of the working group co-chairs on behalf of Korean Forum. Let me open our sessions. Firstly, I would like to introduce our working group briefly. This is our second working group meeting after
เสร็จเนี่ยภายใน17 กันยา 2565 มหาลัยเทคโนโลยีสุรานารีเป็นผู้รับโครงการนี้นะคะเดี๋ยวขอชี้แจงท่านกรรมการเพื่อทราบว่าคือเนื่องจากที่ยังเพิ่งมาตรวจรับเนื่องจากมีการแก้ไขขอบเขตการจ้าง
Can I keep on? Okay. Firstly, I would like to introduce our working group briefly. This is our second working group meeting after approval of the APAN board. As you know, these days AI technology is very hard. Many people try to apply AI technology to various areas. We can also recognize many activities to apply. I'm sorry. Anyway, so we decided to organize a working group in APAN in order to share experiences for development of AI-driven activity for networking as well as its deployment. Our history is as follows. The history is very brief, but our first and second BOPON meetings were held in APAN 50 and 51 respectively. After approval of APAN board, we had the first working group sessions at APAN 52 last year. From the advent of our working group, Dr. Hidehisa Nagano from NIST Japan and Professor Hwang Jia-hong from BUPT China have contributed to our working group as co-chairs with me. While preparing our working group meetings, I have experienced AI-driven technology is still in the early stage, but as NRNs can be used for research and education, I'm very sure that our working group can contribute to APAN community in the aspect of network technology. Today, we have 8 presentations during 2 sessions. The speakers are from ESNet from United States, NIST from Japan, China Unicorn Research Institute, Nankai University, National University of Defense Technology from China, and Korean Forum, CodeJ, KT, Jeju National University from Korea. I hope we will have a very good time today. Thank you very much. The first session chair is Dr. Hidehisa Nagano from NIST. Hide, is there?
Yes. Okay, I'm here. Oh, can I start the first session?
Yeah.
Okay. Oh, so yes, let's start the first session. I'm Hidehisa Nagano from NICT, and the first speaker is Dr. Mariam Kira from ESNet, and the title is Using Deep Learning to Improve Data Transfers for WAN. So, are you ready, Ms. Dr. Kira?
Miriam was unable to make it due to family emergency.
Uh-huh.
So I will be doing the presentation this
Okay,
evening
yeah.
or this morning,
Okay.
or
Okay.
depending on where you are.
Yeah, that's okay. Thank you. Please start the presentations.
Thank you. I appreciate that. Let me share my screen. Hopefully I can. Okay. Can everyone see?
Not yet.
Okay,
Yes.
now I see.
Okay. Participants can now see. Excellent. Thank you. So deep learning, using deep learning to improve data transfers for WAN traffic. Let's see if I can get this. Oh, amazing. Yay. Sorry, Zoom is a little, it sometimes works funny. Miriam, Nick, and myself are all work at ESNet, Energy Sciences Network, which is a network for the Department of Energy in the United States that supports kind of scientific missions. And one of the things that we're working on is an attempt to build an application which provides optimization for WAN network traffic using machine learning. And this is an artificial intelligence. This is a presentation on that. So the premise is that networks have become increasingly important, particularly since the pandemic began. A lot of the needs about flexibility have become extremely apparent. And so the challenge is, how can we optimize network resources, i.e. large, expensive WAN links, to adapt to workloads fairly dynamically. And so we're looking for a data-driven learning solution that can help learn patterns across multiple links and improve network protocols and their performance. One of the problems that we run into with this general challenge is that the usage patterns, while are generally fall within certain behavioral characteristics, they are fairly unpredictable. Network topologies are large and complex, which leads to kind of complex system issues. And then with the devices that we're using, kind of a classic router, there are restricted capabilities on these devices. So kind of to set the stage where we are now, networking today, kind of like where we started years ago, was, we have deterministic routing algorithms, kind of standard BGP, ISIS, and the like, require significant amount of manual setups. When things become problematic, you get congestion and packet loss. TCP, which is the primary transport protocol, is sensitive to congestion and packet loss, which leads to significantly decreased performance. To help buffer against that, you have to have inefficient utilization by necessity. If you run all of your links at 90, 95%, you'll get terrible performance. And we can't. That's the exact opposite of what we need. So the self-driving network, as we are attempting to build, uses an adaptive traffic advisor, which means it looks not only at the current state and health of the network, but it looks at historical patterns. And it's been trained to avoid congestion and packet loss. This lower congestion leads to better TCP performance and allows for higher utilization because the adaptive traffic advisor has learned kind of patterns and characteristics of higher performance solutions. And this does lead to some better fault conditions as well. So the general pattern, the general feedback pattern is the agent receives, the agent is the little green robot. That's our tool The environment is the maze, which represents the WAN. The agent receives state from the WAN in the form of information about congestion, about jitter, about packet loss. It provides an optimization solution given the current health of the network and historical behaviors. It feeds that action back into the network. And then in kind of a classic feedback loop, there's a reward policy value feedback where we kind of work on optimizing solutions. The name of the project that we're working on is Heke, which is the name of a Greek goddess of crossroads and magic. It just seemed kind of appropriate at the time. And it's we describe it as a smart solution for high performance networks. And to kind of reiterate some of the things I mentioned before, the pandemic highlighted the importance of networking in kind of day-to-day science, particularly given how people have to work remotely. We have to deal with surges in traffic, both in terms of highly performant data movements, as well as highly interactive things like Zoom sessions. The network is heterogeneous in nature, and as suggested, and probably things we all know, latency loss and congestion can dramatically impact network performance. Because every network is different, the traffic is different, we need the solution we're looking for will attempt to take into consideration that and avoid the need of constant human attention. And depending on what your desires are, or kind of the network performance characteristics that you're looking for, you might optimize for latency or hotspots, or avoiding failures or avoiding congestion. And you should be able to optimize to provide a solution for one or more of those as needed. So kind of how it works. There's no compromise on performance, which means it's not something that sits within, it doesn't sit in the traffic flow. It generates its solutions via network health activity. It learns traffic classes based on, sources and destinations. And it kind of looks at long-term historical characteristics as well as short-term network health characteristics. The passive and active learning that it takes into consideration, I'm going to go into some detail about the types of data that is fed. So the passive is the historical network health data, which is typically NetFlow. I'll go again more details later. And active learning is perf sonar information. And we're currently building a hardware solution for this as well. So kind of like a mechanism written in P4, which will be able to provide high-speed solutions for the problem. And this is just kind of a reiteration of the feedback loop, where you start with an observation with network telemetry. You provide a solution for an optimal solution, and then you feed back to the forwarding tables, flow rules. And what we're going to be using is segment routing in ESNet, so we'll be able to kind of set the forwarding characteristics in essentially just like a forwarding matrix. And then depending on how effective that is, we'll have a feedback loop for the reinforcement learning component. So looking at what it is that we use for the observation, the site characteristics. So what we're using as kind of like endpoints are the different national labs. And their network characteristics don't tend to change very fast because it involves lots of humans doing basic work things. And if a supercomputing facility will not change its traffic characteristics much, nor will an instrument of some kind. And so the site characteristics have slow update cycles. And essentially, we just take the traffic classes and we break them, the traffic that we see, and we break them into 3 classes, which are like jumbo transfers, which are just large data transfers, interactive traffic, which is kind of like the Zoom sessions we're having now, where there's a lot of short interactive sessions. And by sessions, I mean either connections or flows, depending on kind of how you like to think about it. And then there's just kind of a default traffic class, which is neither highly interactive nor particularly large. To generate these site characteristics, we look at historical net flow data, which is in our case sampled 1,000 to 1, and we typically look back some number of months. And the characteristics that we derive are a function of both time and data volume. The other thing that we use in the observation class of information is link characteristics. And for that, we use the perf sonar, because it's a kind of an always on interactive way of judging the health of your network. And has a very fast update cycle, particularly link characteristics have a fast update cycle as compared to the sites, which are really slow in changing. What we're looking at now is just kind of like loss, delay, and jitter as the fundamental characteristics of like a healthy link in our WAN network. And this is simply just time series data. So it's not data volume necessarily, it's just kind of a stream of health information. The data analysis that we use this is just kind of standard unsupervised clustering, and it's fed into the kind of the real-time AI learning, as Miriam likes to call it. So looking at these, the sites, when we see them, we kind of look at the table on the far right. We break a flow down into 9 characteristics, whether, depending on how long it lives and how much data is moved around. And the numbers there are just kind of a way of identifying them. And the darker the color, the more rare that it is, or the more common it is. Apologies. Let's see here, the manual. So in identifying what constitutes large and small and short and long, currently we use a manual scale selection, but that is something that we're looking to just put into kind of an auto scaling mechanism in the next version. But just to get things going, it seemed like a good idea to start with something, because we know the statistical characteristics. And so figuring out what large and small are is not super difficult. And so we take this data and we create kind of a clustering analysis. And we cluster in terms of space and we cluster in terms of time. And by space, I mean kind of like a data volume. So we look at the data volume, I think of that as a space component. And we look at the data duration, we think of that as a time component. These 2 images are just a 3D representation of the clustering that happens. The one on the left is the time clustering. And we take the flow records, we process them, we run them through the clustering mechanism, and then we identify groups of flows, which are, each of the 3 different classes. And this is all unsupervised clustering. So each run of the site analyzer is independent. Looking at the links, the data is a lot more transient than the site data. And as mentioned, we use perf sonar to continuously measure the network health. We define a connection between 2 endpoints consisting of a minimum of 2 flows. Sometimes you have multiple flows if you have like a lag connecting sites and you need, a higher bandwidth. But one thing we identified is that link characteristics are not directionally symmetric. Just an example of that is the loss graph or the jitter graph to the right. In one direction, you have the pink or the fuchsia, and in the other direction, you have the green. And so you essentially, you have a much smaller standard deviation for one than the other. which is kind of interesting. So you can't just say this link has these characteristics. You have to say this direction of the link has these characteristics, which isn't a big deal at all, but just good to know. And again, we look at loss, delay / latency, and jitter. And adding more components is not difficult at all, and something that both perf sonar and the type of analysis will support. We're just starting with these 3 basic network health identifiers. And this is just a review of the cycle. I'm not going to spend much time on it because I'm running out of time. And so an architectural diagram of what it is that we, what we have is, and how we're going to use it, is we start at the top with a Hecate. And we have the simulation engine, which is the stuff that Miriam is writing, which provides the optimal solution. We have the traffic class identifier, which is the clustering that we just walked through. The conductor is a tool that is fairly flexible. In this case, we're just using an API to a segment routing mechanism, but it could be almost anything, really. We're building it modularly, so you can kind of take out different pieces and replace them with others. In this case, the conductor speaks to a PCE. You can do a different kind of segment routing. You could have it talk to an SDN controller, or you can even do like QoS and kind of traffic engineering classic. Currently, it's all running in software, but we are building an FPGA with a piece of software in F4, which will provide a much faster turnaround time in the simulation engine. And then essentially the box on the left is just kind of the tool. It is deployable and installable. The first prototype is we're kind of playing around with it now, and it's been tested on Raspberry Pis. There's a version of P4 for Raspberry Pis. It's not performant, but it allows you to kind of explore the solution space. The second prototype, we are not there yet. It's faster inferences being transferred to FPGAs for classification at the edge and flow level decisions. So we're hoping that we might be able to do kind of a distributed solution for this. But today we're just kind of prototyping the Raspberry Pi as well as doing passive learning in simulation. An example of what we did a demonstration at SC at supercomputing in December. And so we just created kind of a toy network using 4 routers, different traffic classes, and link characteristics. And the link utilization was what we were trying to optimize for. So before, link 4 was the troublesome link. If looking at this, this is a terrible slide. One of these links is link 4, and it was operating at significantly greater than optimal capacity, in this case 34.8%. We ran this through our solution, and the traffic balancing was significantly better after just one iteration. And so the traffic on link 4 went from 34.8% to 17%, and it was kind of spread out across other links because we were optimizing on utilization. So DeepRL is an extremely effective reinforcement learning is an extremely effective method to allow systems to learn, to self-manage. There are challenges such as hyperparameter sensitivity, which is really can be quite problematic. Leveraging model-based learning, such as traffic prediction. One of Miriam's other projects is NetPredict, which is a really interesting way of modeling traffic behaviors and allows you to predict ahead of time, which is really interesting. So it does active learning in that you can, if it needs to retrain, it's not a big deal. It's just kind of built into the way that it's processed. And the reinforcement learning is currently deployed and experimentally into a GPU FPGA, and will be one of this year's projects is to make it is to actually roll it onto a FPGA proper instead of a simulation, which will vastly speed up the solution time. And that, I believe, is it. Do you have any questions?
Hi, Mr. Javier. Yes.
I have a question. Can I ask?
Yeah.
When you are presenting a difference between a self-driving network and other network, you're saying that it will avoid the traffic congestion. So you have designed any specific protocol for that, or you have any technique? How can this can avoid the traffic congestion?
Can you please repeat the first half of your question? I'm sorry, I had my audio turned way down. Can you hear me?
Yes, I can hear you.
Could you please repeat the first part of your question? The audio was turned way down and I couldn't hear you.
I am saying that, is there any technique that you have? How can, in the self-driving system, how can traffic congestion be avoided?
So if I understand your question correctly, you're asking how can traffic characteristics be like traffic? How can problems as described by characteristics be avoided?
Sorry, I cannot hear you clearly. There is some problem.
Actually, the question is, Doctor, that he wants to say this thing that, for example, you have mentioned this thing that self-driving network is avoiding the traffic congestion. You have explained this thing in your first talk, but he's saying that have you managed to define some kind of protocol, or reinforcement learning by itself is doing this thing? Avoiding. Yeah, this is the question.
Thank you. The reinforcement learning is doing all of the heavy work as far as solving the solution for the optimization. Does that answer the question? And if not, I'm super happy to take this to email as well.
So
Yes.
actually, I also have one question about your previous figure in which you have shown the link utilizations
Yes.
of a link, which was heavily loaded in your first diagram, and in the second diagram, the link utilization of that link was reduced. But if you see that in the other end, there was link 1 that was getting the more traffic. So before and after. So it's just shifting a traffic from one link to the other link. So it seems to me like this. You can see the link 4's traffic is reduced, but if you see link 1's traffic, it increased heavily.
Yes, that is correct. Each of the links, it was hard to take this information from the map, and I think we're going to update that slide, is each of the links had different characteristics, some, as far as bandwidth, as well as latency and data loss. And so essentially, and this is kind of a toy solution. So it's not something I would plug into our network yet, but the idea is, definitely link 1 picked up a significant amount of the traffic, but in I think the idea is that it wasn't before. And so we kind of found a solution to spread the traffic out more efficiently.
Yes.
I very much understand your question, and this isn't a very satisfying example, but it is the currently the one we used at SC, and so we have we kind of went with it.
In other words, we can say that reinforcement learning works in its own mysterious way to achieve the goals.
Yes, I suppose.
Oh, sorry. Could you hear me? I was going to ask a question also. Yeah, my name is Javier Diaz. I am from Jeju National University. I just have one question that maybe it had already been answered in one of the slides, but I could not see it. We're talking about the reward for the deep reinforcement learning. And as we know, I mean, we are analyzing a complex state of the network. So what type of rewards are, is there some kind of policy to give some weight for the rewards in order for achieve like a good optimization? Because I guess it will not be done by just providing latency or something like this, right? The reward itself. I think there should be some sort of weight that needs to be done, or some other type of considerations in order to provide a good reward to the reinforcement.
Yeah, absolutely. I think rather than providing you with a poor answer, so this is why Miriam was supposed to do the presentation, because that is her component. If you can email the question to either me or all three of us, we'll get back to you as soon as possible with a detailed answer.
Thank you. Thank you.
But I don't want to give you a half answer, because that seems, rude.
Thank you very much.
Yes, thank you for the question.
Questions? So it's time to go to the next presentations. Oh, thank you, Scott.
Yes, thank you. I appreciate everyone's time.
Okay. So the next speaker is Dr. Kafle from NICT. The title is Network Control Automation Standardization Activities in ITUT. Would you please start the presentation, Dr. Kafle?
Yes, thank you. Thank you, Chair, for the introduction. Can you see my slide?
Yes.
Oh, good. And I'm making it full screen.
Yeah.
Okay. Good morning, good afternoon. My name is Ved Kafle, as introduced by the Chair. And today I'm going to give you some information about network control automation standardization activities in ITUT. And this the outline of this presentation is as follows. First, I will be showing you some overview. Then I'll be focusing on the ITUT 2 focus groups activities. One is focus group on machine learning for 5G, and the other is the focus group on autonomous networks. And then I'll be providing you overview of ITUT recommendations and work in progress deliverables related with the AI-driven or network automation, and then finally conclude this presentation. So AI-driven network activities are mainly progressing in the ITUT study group 13, which is responsible for standardizing network architectures and the requirements, frameworks like that. And there are 2 focus groups. So one is focus group on machine learning for IMT 2020 or 5G. This focus group has already finished, but it has produced many deliverables. And the other focus group, which is currently running, which is currently active, is autonomous networks focus group. And it is also producing deliverables on network automation by using AI and machine learnings. So this slide shows the activities that have been conducted in ITUT. So starting from 2017, from the establishment of focus group on machine learning for 5Gs, and then currently in 2022, we have a focus group on autonomous network. So let's see what every year has been done. In 19, focus group on machine learning 5G submitted 3 deliverables to study group 13 to consent as 1 supplement and 3 recommendations. Maybe you are already familiar with the ITUT standards. Those standards are called recommendations in ITUT terminology. And in 2020, focus group on machine learning for 5G finalized several deliverables, and it also initiated AI in 5G challenge projects. So these are the projects being called openly, and the participants from university or different organizations can propose AI driven activities or the network activities. SG13 published several recommendations in 2020, which I am going to show you in the next slides. And then in 2021, focus group on autonomous network, FGAN, established, and also ITUT SG13 produced several other related recommendations, and they are also being progressed recently. And then about the FGAN is autonomous network focus group. It's studying use cases, gap analysis, requirements, architecture, framework, trust, etc. in starting from 21 to till now. And this slide shows the list of ITUT recommendations based on focus group on ML5G. So as I mentioned earlier, ML5G studied architecture, interfaces, use cases, data formats, performance evaluation, security, etc. of AI-driven or machine learning-driven networks. And the list is here. It produced the use cases deliverable, which has been published as supplement 55, and it also produced the framework architecture document for using machine learning in networks, which is Y.3172, and the other one is Y.3173, which is related with intelligence level evaluation of network. And the 3174 is related with data handling. 3175 is related with the quality of service assurance. And 3176 is related with machine learning marketplace integration. And there are others also, which I'm going to show you shortly. And the focus group on autonomous network, as I mentioned earlier, it was established just last year, and it has been progressing work on use cases, architecture, trust, proof of concepts. And the key concept of autonomous network, which this focus group is concentrated on, are exploratory evolution, real-time responsive experimentation, and dynamic adaptation. So through the integration of these components or these concepts, autonomous network management can be achieved. And in the scope of this focus group, there are several items such as definitions, gap analysis, use cases, enabling technology, guideline for high-level autonomy, proof of concept requirements, and architectures. Then let me show you some of the related standards produced by ITUT. The first is ITUT recommendation Y.3172. It's the architectural framework for machine learning in the future network, including IMT 2020. Maybe you are already familiar with the term IMT 2020. It's ITU's term for 5G network. So this is the simplified architecture framework. It has mainly 4 components. The component shown on the left is machine learning functional orchestrator. It's the management unit. And there is a machine learning overlay, which has 2 components, machine learning sandbox and machine learning pipeline. Actually, these are the machine learning components which collect data, analyze data, apply some policy, and then make some decision. And those decisions can be orchestrated to the underlay network through the orchestrator. So this is the concept of this machine learning overlay, which I'm going to show you in the next slide. So this sandbox is just like the training environment for training and testing machine learning models. This is the sandbox. Then we have the machine learning pipeline. It's the set of machine learning models and the execution abstraction. So it has a number of elements arranged in a cascade, and they perform the task collectively, which I'm going to show you in the next slide about the pipeline. And the management unit, as I mentioned earlier, this functional orchestrator is the management and orchestration. And we have the underlay network, which is the physical or virtual network, for example, 5G network. And to show you in detail about the pipeline system, there are several components. Those components are having input and output interfaces. For example, here the source is the data source, which is collecting data from the underlay network. Then the source, the data is collected by collector, and data is being processed by PP, and then the data will be provided to some machine learning model. And after processing or to process the data, we may apply the policy, and we get some results. The result can be distributed to different components by distributor, and the results can be given to the sink, and the sink will apply the results to the underlay network. So this is the concept. And same pipeline, similar pipeline can be placed in the sandbox here subsystem, which is for the training of the machine learning models. And in the orchestrator, we have this machine learning intent and machine learning functional orchestrators. So these are the management units. This is the overview of the machine learning based network control architecture. It can be applied to different types of network. One example is its application to the 5G network architecture. So this slide shows how the different components of the machine learning models can be integrated with the 5G network architectures. For example, in the user equipment, we may have the source to collect location information. Then we may also have the similar collector in the access network to collect channel measurement information. And then we have a collector in the core network to collect the data. And different types of data are collected, like the packet information from the gateway and the other information related with the sessions and resource allocation from the core network. And they are analyzed, and the analyzed results are provided to the sink for making some scheduling decisions or executing the decision in the packet scheduling. So this is one example of application of the machine learning based model for the control of the 5G network components. Similarly, there are other recommendations. The other recommendations which is dealing with the evaluating the intelligent level of the future network is 3173. It's presenting or discussing the evaluation methods and also presenting the architectural view. And this is important for the network management, or to evaluate the intelligence level of the network management system. And because it provides some sort of like unified concept and the framework for the industry. And it also provides a decision mechanism to the operators, equipment vendors, and the other network industry participants for planning of the network technology features and the product roadmap. So for this purpose, evaluation framework is very important. And in the evaluation, there are different dimensions of the intelligence. So the dimensions are listed here. There are 5 dimensions: demand mapping, data collection, analysis, decision, and action implementation. So these means like demand mapping is something like the representing the requirements of the intelligence, or the defining the components where intelligence are required. And then for that purpose, after that, we have the data collection, we have the data analytics, and then based on the analysis, there would be the decision, and the decision has to be executed or the implemented. So these are the common intelligence dimensions or the steps. And in the execution also, we have different steps. For example, if we think of the workflow, we may have the planning, deployment, maintenance, optimization. And if we think of the subsystems like the network element, management element, network application platforms. So all those subsystems require intelligence. And whenever we say some network is intelligent, then we have to specifically mention which components, which workflow parts are intelligent, or all of them are intelligent, or which subsystems are intelligent, and which functions are intelligent. And in case we make all those functions intelligent, then the overall network system would be intelligent. And let me skip this slide. I'm going to show you a chart. So let's say action implementation, data collection, analysis, decision, and the demand mapping. As I saw earlier, these are the intelligence dimension. So when in the manual operation, all these functions are all carried out by human, right? In the assisted operation, some functions are carried out by human and system. For example, action implementation, it's like orchestration, or the providing some instruction from the orchestrator, and the reconfiguration of the network or the parameter setting is taking place automatically by the system. And then the level 2 is a preliminary intelligence. In this case, action implementation will be fully carried out by the system, and the other components, some are carried by human and system, and some by human. Currently, the networks are targeting for this level 3 intelligence. In this case, we can call it intermediate intelligence, where action implementation and the data collection would be fully automated, would be carried by the system, and the analysis and decision would be supported by human to the system. But the demand mapping, I mean the requirement analysis or requirement setting or the definitions would be written by human. And then the advanced intelligence level, most of the things would be carried by system, and the full intelligence, everything would be carried by the system. So this is the final target for the autonomous network level 5. The other recommendation, other document is Y.3174. It's talking about the data handling to enable machine learning. As we know that data handling is very important for AI-driven networks. So data handling framework is very, very important. So it defines the high-level requirements, and also discuss a framework, and provides guidelines and example use cases. It has listed several requirements, and those requirements are categorized in terms of the input data collection, processing, and the data output. And this is the framework. So in the framework, like the data we have the data repository system, and it defines data models and the API to access the data. And this is the generic representation, but for some specific representation of the model, we may have more models here. And in the control plane and the data plane, again, we have the some broker of the control plane, and we have the broker in the user plane. And as I mentioned earlier, there may be some data model and API specific brokers and the system to access the data. So this framework has been defined and discussed in Y.3174. Next is Y.3175. It's about the architecture of the quality of service assurance. It indicates where the data collection or data sources components need to be integrated, and what other functions of the machine learning or intelligence need to be integrated in different parts. For example, in the user equipment, we need to collect data, and in the access network, we need to collect data, as well as we need to execute the decision, for example, channel assignment. And in the core network, we have the various pre-processing, decision making, and then the execution like that. So all those things are described in Y.3175. And in Y.3176, it's about the marketplace integration. As maybe you are already familiar, ML marketplace is a repository for ML interoperable AI models. So in the future, we may download the machine learning or AI model from the marketplace and then retrain them by using the environment that we have or the data that we have, and then we can apply them to the control of the network, our network. So these operations have been defined in the marketplace. And if you see the diagram, so here it mainly defines the interfaces, because whenever we want to have appropriate machine learning model or AI model from the marketplace, we should be able to specify what type of model we need and for what purpose, or there might be some requirements. So those things should be able to indicate in the interfaces. So interfaces are very important in order to access, or in order to download appropriate models. And next, I'm going to mention about the Y.3177. It's about the AI-based network automation for resource and fault management. Here, resource management and fault management is very important for the network operation. As we know, it also includes data collection and analytics part, and then the results are given to the action decision, where appropriate network reconfiguration scheduling takes place. So it considers three approaches: resource arbitration, network function migration, and reconstruction of the network, depending upon the situation of the failure that has been detected. So this is again some detail of the failure detection and the recovery, and which is taking place which is being performed by the machine learning models automatically, and it shows some detailed workflow. Next is 3178. It's about the service provisioning. So it means that when some application service user provides application requirements to the service provider, the application requirements have to be processed, and from here some network requirements are derived, and those network requirements are given to the communication service provider. Communication service provider again designs logical network based on the communication requirements. The logical network design may be like the virtual network design, and that design is given to the physical network, and the physical network resources are reserved in order to configure the virtual network of the given requirements. And the network status or the APIs are given in the upward direction so that application user can access the resource of the physical network. So these processes are described in this Y.3178. Here is the detailed diagram how the different steps of the network design and the network status reporting takes place. Next is about the FGAN deliverables. FGAN has so far produced only one deliverable, which is use case deliverable, and it has been progressing the other deliverable architecture framework, which I am going to mention very briefly. For the autonomous networks, there have been 40 use cases listed, and their requirements are also listed. They have been categorized, prioritized, and described. Some examples are like import and export of the knowledge of autonomous network, configuring and driving simulators for the autonomous components. Like there are also many 40 use cases. So if you are interested, please check the website. And the architecture framework for autonomous network has been progressing. As I mentioned earlier, its main components are exploratory evolution, real-time online experimentation, knowledge base, and dynamic adaptation. They have been placed in this order with some interfaces in between. And let me tell you what the different components are very briefly. Exploratory evaluation subsystem is the system which can generate or which can like the decide the suitable software controller from the available software modules. And then the other is real-time online experimentation system. It performs experiments in different stages like simulation, test bed, or the other canary test. And it based on the experiment, it decides about the suitability or the fit for the purpose of the controller model. And those models are then again given to the dynamic adaptation subsystem. And dynamic adaptation subsystem has again the two processes. One is the curation process and other is the selection process for selecting the most suitable or the appropriate AI-driven controller. And that controller is being applied for the managed entity to manage the entity. So this is the concept, and the controller is dynamically updated in the autonomous network system. So finally, to conclude this presentation, ITUT has been studying standardizing many components related with the AI-driven network. So far, it has studied gap analysis, use cases, requirement, proof of concept, architecture, trust, data models, or the evaluation framework. And it is also producing several work in progress deliverables. Thank you.
Can I ask a question, please?
Yeah, okay, please ask the question.
My question is regarding NWDAF. Basically, the network data and analytic function was also proposed as a machine learning function that could learn for networks. So my question is that what is the stance of ITUT regarding NWDAF? Does it considers it as a major function, and where does it? Yes, thank you. That is my question.
Would you please again mention end of what?
NWDAF, network data analytic function.
Okay. Yeah, this is, I think you are referring to 3GPP architecture, right?
Yes, yes, yes.
Yeah, that part is very important in ITUT documents and have been referred several times. Let me go to this one. So here it's some sort of breakdown of NWAF because we collect the data and then we do some pre-processing of the data. And then after pre-processing of the data, maybe we further analyzed by the machine learning, like regression or classification, prediction, or the generation, whatever we do. And then we apply the policy. And then based on the policy, we get some sort of conclusion, conclusion or the control decision that would be given to the distributor. So all these functions are depending upon the data, collection of the data, processing of the data. So closely related to NWAF, but NWAF has not been directly used in ITUT documents.
Thank you so much.
Hello, I would like to ask a question.
Yes, please.
Yeah, I am Afaq Mohammed from JD National University. Thank you for your informative presentation. I would like to ask a question from the slide that you showed, the intelligent network chart. I think it was slide 10 or 11. Yeah, this one. So here you have showed some layers, for example, layer 0 and level 5. And you said that some steps will be performed by the system and some by human. So, and you said that we are currently on layer 3. So my question is, HC has already proposed zero-touch network service and management. And as far as I understand, zero-touch, it should provide, the system should provide all the steps, configuration steps. So that should be layer 5 currently. So isn't we are currently currently on layer 5 instead of layer 3, if you consider that HC ZSM proposal?
Yeah, thank you so much. Yes, ZSM, as you mentioned, it's a zero-touch network service management. Of course, if we achieve, if we realize the framework being envisioned by ZSM, we will definitely reach to level 5. But that's ZSM framework is just the framework. We still need to realize the components being proposed there. So that's why we are not in level 5 now, but rather we are targeting to reach to level 5 by achieving all the, by developing technology related to all the components. But currently we have the technology for level 3. The current technology can support up to the level 3, but gradually new technology would be developed and we can move to level 5, hopefully in next 10 years or sooner.
Okay, so you mean that ZSM is currently not fully implemented, it's just a proposal?
Yes, yes, all components have been not implemented yet, but
right,
some of them are.
Okay, thank you very much.
Hello.
Yes.
Can I ask a question?
Yes, please.
So first of all, thanks to you for the presentation. And I have a question that if you have written some documentation in regards to Internet of Vehicles in 5G, and specifically in the domain of autonomous networks of vehicles.
Yeah.
Do you have some documentation related to it?
Yeah, for the autonomous vehicle, there are, of course, ITUT is also working on that aspect. But today I just prepared a document for the autonomous management of the network, not of the vehicles. But of course, vehicle network or the autonomous, what we call automated driving requires network support, and that network support the system need to be managed autonomously. So somehow related, but not directly addressing the question that you have asked. I can provide you offline information. Please send me your email.
All right, I will share the email in the chat section. Thank
Okay,
you.
thank you.
Thank you very much. So it's time to go to the next presentations. Thank you, Dr. Kafre.
Thank you so much.
Yeah. And the next speaker is Yu Weijie from China Unicom Research Institute.
Okay, thank you.
And the title is
I will share my screen.
Yeah, yeah.
Okay, can you see my screen and hear my voice?
Yes, okay. It's good.
Okay, thank you.
Please start
okay.
the presentation.
Okay, thank you. Good morning, good evening, and good afternoon, everyone. It's my great honor for today's presentation. I want to take this opportunity to talk about the strong power of AI technology with all of you experts. The topic of my presentation today will focus on the data-driven network intelligent operation. Okay, as we know, in the past 2 years, all over the world are struggling with COVID-19. Face-to-face life, work, and trip are facing much inconvenience. Many of our activities turn to online mode. According to a survey from Ericsson, 83% of the people believe that communication technology has helped them cope with the impact of the COVID-19. 67% of the people believe that reliable connections have helped them to achieve a very convenient remote work. And the number of phone calls and durations, traffic volume, Wi-Fi usage time have all increased dramatically. We can say that the telecom operators have been supporting the normal operation of the whole society with their strong digital capabilities. And also the telecommunication industry has become the foundation of the entire society. It is empowering industries such as education, teleconferencing, and transportation, and so on. Telecom operators are facing huge opportunities. Also, there are much need and opportunities for telecom service. In the 5G era, there are many changes and challenges compared to 3G and 4G networks. First of all, target users change from 2C users to 2B users. For 2B users, personalized needs are more important, and general purpose network service cannot meet user needs. Secondly, the network type and network operation mode are getting more and more complicated. There are 2G, 3G, 4G, and 5G networks coexist. They need to be hybrid networking. What's more, China Unicom and the China Telecom, there are two different telecom operators in China. We are promoting the co-construction of 4G and 5G networks. They share network equipment. Here it is mainly wireless base stations, so that the network structure is more complicated. There are much interoperability and compatibility work involved. At the same time, traditional network is facing transformation into IT cloud networks and even commuting networks. The complexity of network maintenance and optimization has dramatically increased. All of these changes require the network to be sufficiently flexible so that service and response can be agile enough. Telecom operators need intelligent methods for network operation. Under this background, China Unicom has proposed a network intelligent operation architecture to face the opportunities and challenges. The basic capability of this architecture is built through the following steps, which are network infrastructure layer, the data foundation layer, and the intelligent application layer. In addition, the smart ecology is a guarantee, and this architecture aims to achieve the ultimate goal of smart services. This architecture provides a path for digital transformation of telecom operators. Core... Sorry? Okay, I will go on. Can I go on, please? No. This architecture provides a path for digital transformation of telecom operators. The core of this architecture is data foundation and the intelligent application. This is layer 2 and layer 3. In layer 2, telecom data is the basis for all of the following analysis and modeling. In layer 3, based on the AI techniques, a series of intelligent applications are developed to improve the efficiency and effectiveness of network operation. Next, I will give a further introduction of these two parts. Okay, for the data foundation layer, I will give a brief introduction to telecom data. Telecom data is a gold mine for telecom operators, which is also the basis for all of the intelligent applications. Telecom data is well ahead of other industries in geographical scope, time span, and user scale. In China Unicom, most of the telecom data is generated from network operation and business operation, like the operating system, manage and maintain system, network and interface collection, and targeted testing. In China Unicom, telecom data is mainly classified by domains, like BSS domain, OSS domain, decision domain, management domain, and e-commerce domain. Among these domains, BSS and OSS domain data are the most important categories in China Unicom. It implies accurate information about user characteristics, user location, user behavior, user experience, network operation status, and network tendency, and so on. Okay, next, I will give a brief introduction of the BSS domain data. BSS domain data is generated from the users and business operation. BSS domain data is a collection of multi-dimensional data. It mainly implies information about customers. Mainly implies information about customers and business operations, including the user information, customer information, product information, and the marketing information, and so on. For the OSS domain data, it is generated from various systems, platforms, interfaces, and links during the network operation procedure. The OSS domain data records rich information about networks, users, and services from multi-dimension. As for the advantages, compared to other data, it is more detailed, lower in sensitivity, lower in latency, and higher in accuracy. Typical OSS domain data include the trace data, MR, MDT data, CM and PM data, DPI data, and so on. Due to the time limit, I won't go into the details here. Okay, let's reach the intelligent application layer. In this slide, I will introduce some intelligent applications which have dramatically improved the network quality. As we know, the transformation of 5G network architecture and the business characteristics brings challenges to operators' network operation, maintenance, and optimization, and it's more difficult to locate network problem. Based on the fusion application of OSS and BSS domain data, China Unicom has built an automatic system. As shown in the network lifecycle diagram, the modules highlighted in orange color is the intelligent applications. Through these intelligent applications, algorithms, models, components, and platforms. It can achieve automatic network operation status monitoring, precise location of network problems, and the root cause analysis of the network problems. In this slide, I will introduce some intelligent applications, and they mainly focus on the needs from the marketing and customer service department. First of all, it will build the underlying basis capabilities. Fundamental analysis covers user experience, user portrait analysis, user preference analysis, and so on. For example, if the user is watching a video program, it will evaluate whether the network service can meet the user satisfaction. With user portrait and user tagging analysis, in this part, it will describe users from different dimensions and tag the users with its most obvious characteristics, like film fans, game fans, and so on. After that, we can develop a series of applications to meet different demands. For example, we can focus on mobile users and build a traffic usage model and analyze and predict their preference at night and weekends so that we can recommend broadband to target users. We can also analyze the consuming habits and service usage habits of the user so that we can recommend 5G network product package to precisely meet the user's demands. In network intelligent operation architecture, the data foundation part focuses on mining the implicit information in telecom data through data parsing and data fusion, so that we can amplify the value of the telecom data. In the intelligent application part, it focuses on developing intelligent application with the help of AI technology, so that we can promote the efficiency and effectiveness of marketing and customer service. All of this work helps telecom operator to build an agile network with simple operation and maintenance, which can provide flexible business. This can promote the digital transformation of telecom operators. Nowadays, digital transformation has become an important task of the whole society. Telecom operators can provide the fundamental network connections and network services. We are very pleased to promote the industry, academia, research cooperation, and we can complement the advantages of production, education, and research, and then promote the digital transformation of the vertical industries and realize a win-win result. Okay, that's all of my presentation today. Thank you very much.
Are there any questions?
Okay, and questions? Okay, thank you very much. If you have any questions, we can discuss it offline.
Okay, thank you very much.
Okay, thank you.
Yeah, and excuse me, I cannot hear you well, Dr. Muhammad. Do you have any question?
Actually, I have a question.
Okay.
Thank you. Thank you for your the presentation. It is a very simple question. What kind of the platform do you use actually? In my lab, we usually use the OSM open source manual. Then I think if you deploy the network virtualization system I think you should assume some platform to orchestrate several functions. So do you have any specific platform to orchestrate and manage the systems?
If I understand correctly, do you want to ask the platforms to improve the intelligent operation?
Yeah.
Right. Okay. We divide the intelligent applications into two parts. One part is aimed to improve network quality improvement, like shown in this slide. And another part, we use intelligent applications to improve the operation efficiency to meet the needs for marketing demands and customer service demands. And I showed the application in the diagram, like highlighted in the orange color. We use these applications. Okay, it is embedded with AI, machine learning models and algorithms. These applications can help telecom operators to monitoring the network status and precise locate the network problems and also take out the root cause analysis of the network problems.
In the another aspect, my another question is, I think we can assume some the network controlling system. Actually, I think SDN could be assumed for the virtualized network system. And I think your system is based on the network virtualization. So then can I know what kind of SDN controller or some other mechanism you use?
The network evolution tends to IT cloud, as you say, the SDN mode. And the network evolution mainly implies this layer, the network infrastructure, and the network tends to evolve to cloud network and also the computing network. This is the fundamental of all of the architecture. And the slides in this part, I mainly concentrate on the data and the intelligent application. And the data is come from the cloud network. And the SDN mechanism is not covered in the work of my presentation today, but it is an important, very important task for the telecom operator in China Unicom, maybe other departments in my company.
Thank you.
Okay, thank you.
Thank you very much. Thank you, Rachel. Okay. So let's go to the last presentation of this session. Okay, and the last speaker is Afaq Muhammad from Jej National University. The title is Machine Learning Driven IBM-based approach for anomaly mitigation on calling. Sorry. Are you ready?
Yes, thank you for the introduction. In the last APAN meeting, we presented our work on ML-driven IBM-based approach for anomaly detection. In this meeting, we are going to present our work on anomaly detection, as well as some improvements that we have made in our anomaly detection system and some parts of monitoring system. So the mechanism that we propose for anomaly detection and mitigation, it collects and analyzes flows using machine learning for interpreting traffic patterns. And it also automates the deployment of high-level policies for corrective actions related to the anomalous traffic occurrences. So this whole system is deployed on the Korea Advanced Research Network, which is also known as COREN. And the abstraction is provided by IBM, intent-based networking for network anomaly detection and mitigation in this system. So I'll briefly talk about the smart anomaly detection and mitigation system on COREN. For the goals, we have the first goal set was real-time processing of S-flow data for the creation of network traffic dataset. In our previous work for anomaly detection, we used NetFlow, but we have made some improvements in this work, and we have now we are now using S-flow for the data creation of a network traffic dataset. And then we have a network anomaly detection system based on ML algorithms, which are K-means clustering and KNN classifier for unsupervised and supervised learning. And we also have automatic execution of mitigation policies by leveraging IBM, and also a real-time monitoring system for assurance of network devices. And we also implemented a closed loop system by obtaining information from the infrastructure layers and processing, analyzing, and applying network policies directly from the management layers back on the infrastructure. So these are the 5 goals that we set in the beginning of our work, and we have successfully achieved all these 5 goals. I'll present these achievement of these goals in the upcoming slides. So for the project description, we have, first of all, the network infrastructure, where we have traffic experiments for data collection and S-flow configuration in COREN testbed switches. And then we have ML-driven anomaly detection, in which we process data of, for example, S-flow raw data. And then we have data stored in Elasticsearch indices for anomaly detection algorithm training and testing. And we have then clustering and classification for incoming traffic data for anomaly detection. We use these 2 algorithms, machine learning algorithms, for unsupervised and supervised learning. And then we have monitoring and analytics, in which we use Prometheus and Grafana for showing the network and connected devices status in real time. And finally, we have intent translation engine, with the help of which we create policies and execute by the intent translation engine to mitigate the anomalies. If there is anomaly found in the system, then we can mitigate using the intent translation engine. So for the system description, we have a closed loop approach here for real-time processing architecture that provides the functionality of real-time, for example, message ingestion, first of all, and it gets S-flow data from the infrastructure. And then we feed this data to big data's Apache Spark for stream data processing. And after data processing, the data is then forwarded to ELK stack and Grafana for data analytics, storage, and pre-processing. Then the process data is forwarded to ML-driven anomaly detection system, where we have K-means clustering algorithm implemented first, and then after clustering the data into different clusters, we then classify the data into, for example, normal or anomalous traffic classes. And then comes the policy formulation. After formulating the policy, we give that policy to SDN controller, and SDN controller deploys or that policy back on the infrastructure. So this is kind of a closed loop approach here that we can see in our system. So for the implementation, first of all, we have the COREN access switches, which export S-flow data. We have Prometheus agent here, agents running inside end servers for resource data collection, for example, network and CPU statistics. And then we have S-flow collector here, which receives S-flow data and feeds it to Kafka topics for data processing Spark, which will be shown in the next slide, and raw data collection Logstash. So Prometheus database constantly here, the Prometheus database constantly collects data from the agents here, which are installed on the host, and a Prometheus gateway, which is shown here. It uses the COREN SDA SDI API for switch monitoring, and then we have Grafana that presents the current state of the network on the basis of these data. Then we have Spark processes, which just processes the data for feature extraction and data set reduction. Here, it stores the process data in Elasticsearch and uses the data for training the machine learning algorithms, which we are using K-means and K-NN. And it applies train ML model for real-time anomaly detection here. So we have the anomaly detection module here, and this Spark system applies this model of anomaly detection here. And then finally, if an anomaly is detected in the system, the intent translation tool, this one, creates a mitigation action that is applied to the affected VLAN and executes it using Corin SDI APIs. So this is again the details of the anomaly detection and mitigation system. In some further details, we have, for example, different steps here, starting from step 1, in which we are again collecting S-flow data, and then we are doing the data processing here in this step, and then we have the anomaly detection system here, and as well as the mitigation system, and we also have the real-time monitoring system shown here. So these are the same details which are shown in the previous slide of the implemented system. Okay, then we have machine learning algorithms. For that, we first process the data. We feed this process data to the clustering model, which is a K-means clustering algorithm. And then we have the cluster of traffic distributions. And once we get the labeled cluster data set, we feed it into the classification model, which is the K-NN classifier. And after model training and testing, we get the normal clusters, and which we have the list of normal clusters as labeled classes. Then we have the monitoring and analytics system. The current topology of monitoring architecture is shown here in this slide. So we have Prometheus Gateway and Prometheus DB, which were shown in the previous slides. And using the Corin API, we are collecting data from different switches in Corin. And we also have some agents installed, monitoring agents installed on the host. And we can see that the Prometheus database is receiving data from these hosts. And the switch data is collected from the Corin API using the Prometheus Gateway, and then stored in the Prometheus DB. And we can also show this visualized data using a Grafana user interface, graphical user interface. We have the intent translation tool in our system. First of all, if we have the anomaly detected in the system, then the work of the anomaly mitigation system starts. It identifies the attacks, like source IP of the traffic pattern, and it extracts the necessary value IP address and VLAN ID. It sends this information to mitigation action to IBM as REST API, and then delete flow rule through IBM system. The mitigation is performed by this method using the IBM tool. For experimental details, first of all, we collected data from the infrastructure using our S-flow system. We have the anomaly detection system here, and we have S-flow enabled OVSs. So we generated some normal traffic and some abnormal traffic using these scripts that we wrote for normal traffic generation and abnormal traffic generation. And in this way, we collected data from the switches and on the Corin infrastructure. So first algorithm, machine learning algorithm that we applied was the K-means clustering algorithm. We had in total around 381,000 records. And the K-means clustering algorithm is applied for creating a labeled data set of clustered traffic data. So we have, for example, now clustered data. Before it was unclustered, unsupervised, unlabeled data. So we applied unsupervised machine learning algorithm for labeling the data into clusters, in different clusters. And then we perform the K-NN classifier on the cluster data that we achieve from the K-means clustering algorithm. So we have the classifier that is trained and serialized as a file, and the model is loaded into Apache Spark for real-time anomaly detection here. So we have, for example, K-fold cross-validation. It we have the KNN model, and it is serialized as a file and given to the Apache Spark for anomaly detection. So we have now different classes as a result of this KNN classifier. This is just the basic VLAN configuration on Corin shown here for just the Seoul node. We also have same VLAN configuration for Pangyo, Daegu, Busan, Jeonju, and Gwangju, which are the cities in Korea and or existing in the Corin topology. Then we have the demonstration scenario. First of all, in first step, we have the IBM single touch and play system. Then we have the topology here, which is shown in step 2. We have the deployed scenario, and in step 4, we generated attack from Seoul to Pangyo. Seoul is the capital of Korea, and then Pangyo is a different city. So we generated traffic from one node to another node. And then in step 5, the anomaly was detected using our anomaly detection system, and then it was also mitigated through our IBM system. And here in the military system, we have Grafana for visualization. You can see here some visualized traffic and data. And we have also ELK stack, which can also store raw data in ELK, which is Elastic Log Session Kibana. So this is a demonstration scenario. We had 5 IPERF clients and 1 IPERF server, and there were 5 attackers, which we used for generating the flood traffic using APAN53. And then we created some normal traffic, generated normal traffic using shown as a dotted line here, and also the attack traffic, which is shown as a red line here. So we had the host information, we had the VLAN ID as shown in previous slides, and then prediction probability of belonging to traffic cluster. And then the anomaly was detected, and finally it was mitigated using the IBM tool, which is shown here in this figure screenshot. So now I'll show the effect before and after anomaly mitigation. We can see that the CPU utilization is quite high here, which is around 10% before when the anomaly was detected. And when we applied our anomaly mitigation system, the CPU utilization was dropped again to 0.206%, which is for the Seoul node. So this is how we achieve the anomaly detection and mitigation system. First, the CPU utilization was quite high, and then it was reduced when the anomaly mitigation was applied. So for results, we have the KNN as a classifier. We have used this one as a classifier, and similarly, we have different models here. For example, logistic regression, LDA, and CART, and NB, and SPC. And the mean accuracy of the classifier is shown here. It outperforms almost all the classifiers or all the algorithms here. So it was performed on labeled traffic data collected over 30 days, and this is the output of the k-means here. And then accuracy of anomaly detection. We have 2 classification methods. One is the hard classification, one is the soft classification. We opted for the soft classification method, and we can see that it performs better than the hard classification, because using the hard classification method, this point, which can be shown here, was given to the normal traffic, but actually this was the anomaly. So because we have here different unique IP destination IPs, so this destination IP was shown in the normal traffic if we chose the hard classification. But once we chose the soft classification, it was shown as an anomaly. So this is how the soft classification method was used in this scenario. And then we have the performance of overall system, our performance matrix of detection and mitigation. So we have host, 1 anomalous host, and 5 anomalous hosts shown here. So the detection was in 60 seconds, and then the mitigation was in 2.5, around 2 and 5 seconds, and total it took 65 seconds for detection and mitigation, the whole thing. And when we increased the host to 5, detection was again done in 60 seconds, but mitigation was time was increased in 10 to 15 seconds, and in total it took 75 seconds. So we can see the accuracy here, which is above 90%. So performance of test detection and mitigation time over around 11,000 records of traffic, and spark window does not exceed 60 seconds of processing time. So in summary, the anomaly detection and mitigation system has been applied to intent-based networking. And the approach taken for this research considers the multiple qualities that IBM brings to modern networking systems, such as network abstraction, orchestration, automated implementation, state awareness, assurance, and remediation, which can be utilized for building more resilient systems using this approach. In addition, this approach considers a real-time processing architecture for handling continuous streams of flow data and processing them in real time using high-performance tools like Apache Kafka and Big Data's Apache Spark. So the evolution of the system is guaranteed by the constant collection of processed and raw flow data, which can be used to furtherly enhance the implementation of ML algorithms or other AI techniques. So I have some video demonstration that I would like to show. If we have time, I'll play the 1-minute video to demonstrate our system implementation. So first of all, we have we can see that we have really real-time monitoring system here, and we are preparing for flood attacks in this terminal window shown on the left side. And then we can see the CPU utilization, which is around 2.97 before attack. And after a few seconds, we have the utilization of CPU during the attack, which was 10.7%. And we can see the timer here, which is now anomaly is detected and mitigation is in progress.
Can you?
And now we can see that mitigation is completed. Sorry.
Can you show the video? We cannot see the video, right? Yes.
I think you need to exit the slide mode so that we can see the video.
Yeah.
Okay. Just a second. I cannot and show. Can you see the video now?
No.
Not yet.
I think you have shared only.
Seen because I've played it, but yeah, I've okay. I'll just a second. Okay. Can the video be seen now?
Yeah. Okay.
Yes.
I cannot hear you. Can the video be seen now so that I can play?
Yes, Dr. Falk.
Okay. So this was the demonstration of our system. We can see that we have actually been for attack 5 ports, and we have hyper normal traffic. We have the Grafana shown for traffic visualization, and now we are preparing for flood attack in the left window here. So the utilization which is can be seen here is 2.9%, 7% before attack, and after a few seconds when the attack is performed, we have the high CPU utilization, which is around 10.7%, and then mitigation is in progress by IBM. And after the completion of mitigation, we can see the mitigation is completed and the CPU utilization is decreased again to 3.28%. And we can see here the timer, which is showing 1 minute around 3 seconds. So our system works from detection to mitigation, and it took around like 1 minute, as was shown in the slides. And we can see the normal traffic is again flowing. So that's all from my side.
Thank you very much. So, are there any questions? Oh, can I ask a question?
Yes, sure.
Okay. So I guess the K-means is unsupervised clustering method. So I couldn't understand the how to construct the label dataset for the training.
You mean the label data set for?
Yeah. How did you construct the data set, labeled data set for the training?
Yes. First, we applied the k-means clustering algorithm because we had the data which was distributed, like it was not shown in clusters. So first, we applied the k-means clustering algorithm to specify that data in different clusters. For example, in 20 clusters, for example. So after that, we applied the k-name classifier to classify that cluster data into classes, into labels. For example, the anomalous class and the normal traffic class. So here we can see that we have now data in clusters, and once we apply the k-name classifier, we can have the data in the in different classes. So that's how we perform the two algorithms for clustering and for classification.
So you mean that you assign the label to the cluster? Each cluster?
Yes, the clusters you can see here, it's starting from 0 to 19.
Okay.
So once we have the clusters, we apply the classification algorithm to produce the classes. For example, we have, for example, a cluster shown here, cluster 5, cluster 1. So we can see that this incoming traffic is belonging to which cluster and whether it's anomalous or normal traffic.
Okay, I see. And I'd like to ask one more question. And what kind of the feature or parameters are used for the feature vectors inputted to the clustering?
Yes, actually, we actually showed that in the previous presentation. So we had different features, for example, sum of bytes, sum of flows, some of packets, and unique destination update, unique destination ports that were used as features for clustering algorithm.
Oh, just 5 dimensions, right?
Yes, 5 dimensions in this data set.
Okay. Yeah, thank you.
Okay, welcome.
Any other questions? Questions? Okay, so thank you very much.
You're welcome. Thank you.
Yeah. Okay, then that's all for the first sessions. So maybe I guess we should announce the next sessions. What do you have? What time the next session will? What time will the next session start?
After 10 minutes. After 10 minutes.
After 10 minutes, okay. So just after 10 minutes, the next session will start. So please join the next sessions. And so I really appreciate everyone who joined these sessions. Thank you very much.
Thank you very much.
Thank you very much.
Thank you very much for the session. Now I am stopping the recording.
Thank you. Our second AI-driven networks working group. Then the first speaker is my student and me. Actually, my university has got funding from Teen Collaboration Center. The project is Asia Connect project. We will build the overlay network in the Teen networks. And the overlay network is composed of such as Korea, Malaysia, and Pakistan, and Cambodia. Then we will have a plan to deploy a system as the overlay network. Then firstly, as the first the presentation, my student Tara will present. And can you start, Tara?
Yes, Professor, thank you very much for sharing our information. So my name is Hantal Ahmed, and I'm working as a PhD student in Network Convergence Lab, Jeju National University, South Korea. So the title of presentation today is IBN at Teen. So we are going to deploy a Teen testbed network in different countries through our Asia Connect project. So the title is an AI-driven intent-based networking platform for service deployment with QoS assurance. So we are working majorly on intent-based networking platform, which are closed loop system in which we allow users to provide policy information of the network from a high level perspective as a single touch input, and then users through a closed loop it can translate it to the lower level infrastructure, and then we also assure the service quality using the closed loop in the intent-based networking. So basically in this project our collaborating NOENs are Cohen, Teen, Myran, Pern, and Cameron. And we have the Asia Connect project, in which we have the collaborating universities, in which Jeju National University, we are the principal instructors, and then we have the co-PIs universities as follows. So basically the content of presentation will follow the background, IBN at Teen, ML-driven SDN plus policy optimization, and cloud resource forecasting and policy management, and at the end we will discuss. So basically the problem with the challenges in the network operations are that they are dynamically changing. At runtime, network are drastically changing, and we need to optimize the network operation and change the policies on runtime based on the situations of the network. So there must be some decisions from the central body, for example, IBN, orchestrator, SDN controller. So there are changes that are required in the network to manage the operations of the network that are highly distributed, like Teen network. So if we are taking manual decision following the legacy approaches, we may have under resource utilization or over resource utilization, or we may overload the system by our booking of resources in the infrastructure. So the solution is that we should automate the system. So how to get that automation is that we have proposed IBN system to involve in the very distributed networks. So what IBN system provide is that they provide a single touch interfaces through which user can select a service and orchestrate it on the network. Also, it automatically it's abstraction above semantic. This means that the problem is that usually the network policies are given as a semantic, like YAML, Yang, and this type of platforms. But we considered to provide a GUI interfaces through which user can just select a service and ask the network to orchestrate those services in the IBN concepts. So it is zero touch in operation, which means that it automatically perceive the network situation and update the network while on the dynamically network is changing, conditions are changing, traffic is being forecasted. So it can update the policies on runtime to assure the service quality. So what is the technology that is supporting it is obviously machine learning. So through forecasting of future, we can take proactive decisions in the network. So we know that what is the traffic pattern, what is the CPU utilization, what is the memory utilization, and based on the type of service requested, we can decide the decisions, decide the policies to be activated in the network on the runtime while considering the future situation of the network. So we can deploy more resources, or we can orchestrate best paths, or we can orchestrate different policies in the network based on the forecasting of the ML models. So there are two types of ML forecasting. One is ML-driven SDN, in which we forecast the link utilizations of the network, or we in the network, and we can decide which is the best path for the service to be provided. Specific QoS requirements to accomplish those, we can decide a path that can accomplish that, or we can optimize the networking in the data plane. Secondly, ML-driven clouds, in which we decide that where to locate the resource, or from or how much resources should be provided to a virtual machine, or a service. So there are two parts in this work. So intent-driven semantic policy translation. So for example, we have the policy. So what we can do is that we can translate those to the cloud Vim infrastructure, where we can have different infrastructures and we can generalize. So there can be different SDN controller owners, OpenDaylight or different. So they must have different APIs. So intent-based networking system, what that it does is that it firstly translate from graphical user interface service requests to semantic policies that are generalizable for all the underlying platforms, and then it translates them from semantic to the platform specific policies, which can be translated to different platforms. So which means that it is generic, abstracted from the underlying infrastructure, whichever. Secondly, it can translate the policies for the cloud infrastructures, where there can be different clouds, public cloud, private clouds, or different cloud orchestrator or Vim orchestrator. So for them, we also do the same thing in the cloud platform. So this is our service orchestration using the intent-based networking, in which we are planning to orchestrate the on the SDN part using the machine learning, and we are planning to orchestrate on the cloud part using the IBN system. So the proposal of our team project includes a very distributed environment in which we have 4 partner countries that are universities that are working on it. So in which we will deploy a test bed in Korea using the current network as a provider as the network operation control. And then we have the Myron and from Malaysia. So Malay University will be working on this part. Then we have the Cameron, and then we have the Pakistan PERN network. So they all will be connected using the team network. So we are the proposal of this project is that to orchestrate both the you can say that cloud and SDN part using the IBN system, and automating the orchestration and control of the network using the machine learning. So basically, if we have a simplified view, what we will do is that we will have an overlay network on top of the team network, and we will deploy our JBox setup that is that will be deployed on different location, and each JBox will have SDN control, microstack Vim as an infrastructure provider through which we can deploy different virtual machines of our own specific needs, and we will have an OVS that will be on the overlay network, and we will have different computes. So using this overlay network, we can have tunneling between each network. So each network is on its own, you can say that public IPs. So connecting them through the team is our goal. So we will have a tunneling between the overlay network, and from that we can have tunnels towards our virtual machines on the compute nodes. So after that, what we will do is that through the IBN at team, what is our goal is to monitor the whole network and whole computing resources at the same time, and use big data analytics and train machine learning models to forecast the situation, and based on the forecast situation, we will automatically update the network dynamically. So this is our simplified view of the project. So IBN at Teen architecture follows this architecture, in which we have intent-based networking, translation above semantic from top, from which we can single-touchly provide the type of service from the intent-based interface, and then based on that interface, we can translate those services into semantic requirements for the policies to be deployed. And the policies will be decided based on 2 ML models that will assess the transport network path utilization prediction and cloud resource utilization. Based on the path prediction and cloud resource utilization, what we will do is that we will decide the policies for the transport network from VM1 to E service provisioning, while assuring the quality of service. So if link utilization is really high, we cannot orchestrate on that path. We can orchestrate on a path which has low link utilization for a high quality service. So similarly, to provide the services, we can decide the policies to the intent-based networking in this manner. Then we can deploy those network policies on the network level on the overlay network, and cloud policies on the cloud, the VM resource, CPU memory and storage of each VM based on the type of service and available storage in the compute node, or we can change the compute node based on the condition in the network. So similarly, the testbed scenario on the team network is that we have Korea. In Korea, we have a node, and then Korea is connected to Singapore, which is a central node in the team network. And through Singapore, we can connect to other countries, Cambodia, Malaysia, and PERN. So a JBox includes rack, in which we will have a OVS installed on a computer, and then that OVS will be connected to the microstack VM, and that OVS will be sharing its traffic to the centralized SDN controller that will be available at our central intent-based networking location. So SDN controller will get the policy information from the intent-based system, and it will be sharing its monitoring information to the intent-based system. Intent-based system using machine learning models will update the policies in the infrastructure. So the overlay SDN testbed designed through Teen, actually we have different nodes that we will deploy on the Teen network, and each network will have a subnetwork. Teen is connected. Teen is connecting different NRENs, that is Coren, Cameron, Myron, and PERN. So using those network, we will tunnel the VM. OVS to OVS tunneling will be performed, and then we will tunnel the OVS to the VM at each JBox. So for example, we have a JBox at the Coren network, so we will have an OVS which will be there. So what we will provide is that through the SDN controller, we will tunnel it based on the type of service from which VM to which VM we have to connect. So we can create a tunnel between OVS using our SDN controller, and then we can link that tunnel to the VM that is our one end VM, and then we can tunnel it to the other end VM. So by this way, we can create a testbed, a connected topology in the team, and different NRENs that are connecting there. So this is a view of how overlay networking overlay tunnels can be made between VM to VM for service utilization or service traffic streaming. So next is that we have an app level tunneling using the HTTP tunneling. Actually, the problem in the cloud network is that if we have the OpenStack cloud on a host machine installed, the host machine itself is accessible by outside network, but the virtual machines that we create are in a private network. So what the problem is that these private virtual machine cannot be accessed from the external network. And if we have another private network virtual machine to communicate with other virtual machine, we need a tunneling. So what we do is that for app level tunneling, we have done a HTTP tunneling, which exposes both the virtual machines to each other, and we can request, a service requester can request to provide a service. So a provider can exist in a private network in the cloud. So what happens is that from the service requester, we request a service through the HTTP bridge. What we did is that we connect it to the network, and then the request follows from this network, and it goes to the publicly accessible HTTP proxy. Whenever a request is received by the proxy, what it does is that it requests the network inside the private network to provide the request, and then they provide the request back, response back to the HTTP proxy, and HTTP proxy forwards this request back to the HTTP bridge, and HTTP bridge then forward backs this request to the private network. So we have overcome the problem of non-accessibility of two private networks on the application level using the HTTP tunneling in this approach. So next thing is that VM instance resource monitoring. Actually, OpenStack also provide the resource monitoring, but for our testbed, we also have set up an instance resource monitoring. For example, we have to monitor the different services in the network. So for that purpose, we also use the proxy for monitoring the instance. So we have installed a client inside the VM instance, we have the node exporter, and inside the host, we have a client which forwards the monitoring information to the proxy server, and it stores the information in the Prometheus. So Prometheus keeps calling for the proxy service to provide the monitoring data, and then the client receives this monitoring, keeps sending the monitoring data to the proxy server. So through the proxy server, we can load the data into Prometheus. Why we did that? We cannot directly export the virtual machine instance because it's in the private network of the OpenStack, and it cannot be accessible from the outside because it has a private IP. And so Prometheus is sitting in a standard, in the central position. So we cannot directly export the data, but we have covered this problem using the client server model using the proxy approach. So next thing is that we have monitoring the SDN OVS overlays that can be deployed on different sites in JBox sites. So from the core network OVS, we can collect the S-flow collection, and from different nodes that are deployed at different location in the team network, we can collect the S-flow information, and we can store it in raw form, or we can use big data processing to store it as a process data. Similarly, we can also collect the node exported data from different nodes, and we can store that in the Prometheus DB, and we can visualize it. So there are two types of monitoring: cloud monitoring and SDN monitoring. So why we are monitoring this data? We are monitoring this data to be applied to machine learning. So moving forward, so what we will do is that we will have a ML-driven SDN policy optimization module in which we will collect the monitoring data, and we will train our machine learning model, and using the forecasting of based on the collected data, what we will do is that we will decide the forwarding policy in the SDN control plane. So SDN controller basically usually manages the forwarding policies using the legacy protocols like open shortest path first, and this can cause our link utilization on the shortest path link, or so we need to assure the quality of service. So using this freedom of policy activation by the open flow or SDN approach, in which we have the control plane separated from the data plane. So on the data plane, we can decide the policy using the ML-driven resource forecasting. So we can decide the best link paths in the and we can decide our flow rules in the data plane accordingly. So next thing is ML-driven cloud resource forecasting. So we get the monitoring data from the VIM or from each node or host based on the monitoring data of virtual machine CPU utilization, RAM utilization, memory utilization. We can forecast it, and what we can do is that we can decide the policy of activating where a VM and with what specifications. For example, what should be the CPU allocation: 3 cores, 2 cores, 4 cores, 8 cores, or what should be the RAM 2 GB, 3 GB, 4 GB, based on the forecasting of the machine learning. This will optimize the resource. Also, it will optimize the service provisioning. Also, it will reduce the you can send service timeouts. So the concept is that we have intent-based semantic from which user can request a type of service, for example, end-to-end video streaming service, or it wants to set up a server, file transfer server, or whatever type of application it wants to activate in the underlying network, which can be orchestrated using the team. So it can request intent-based networking, which is abstracted from the graphical user interface, and then on the underlying test bed, we can orchestrate the services using this platform. So on the other hand, on the runtime, ML-driven resource forecasting and SDN-based utilization models will update the policies and will decide the proactive optimized policies for the network on the both end, on the cloud and on the SDN. So both combined, so together we can see that machine learning models will be able to control the network, highly distributed network, and the test bed will be provided using the end-to-end tunneling on the app level or on the compute level. So this is our proposal for IB at Teen and way forward towards the project, that how we will proceed in the design. So we have a testbed deployment in which we will have like STM controller based deployment of OBS only network, and we will have microstatic Vim based deployment of cloud computes. And on the other end, we will use the collection of data, and based on the data, we will train different machine learning models to optimize both the cloud and SDN part in the IBNet team. So that's all from my side. If you have any questions, you can ask, please.
Hello.
Yes.
Thank you for your presentation.
Yes.
I'm Dr. Hitisham from NUST, Pakistan. So I have just a question about the machine learning part.
Yes.
About your presentation. So what kind of data we can expect of this project?
Actually,
I mean,
yes.
this data is like, what is the size of the data and the form of the data? So this is just wanted to know.
Actually, there are two types of data. One is the S-flow metrics that we are collecting from the switches, in which there will be different parameters of the data, in which we have the link utilization, or we have the bandwidth, or we have the latency, or we have the delay jitter. So there will be different parameters for the SDN data, and that will be collected very drastically, because if we are collecting the dynamic data from the switches, so traffic is flowing through them, the S-flow data is really high amount. So that's why we can include the big data processing to pre-process the data, and then based on the pre-processed data, we can train a machine learning model on top of it. Similarly, from cloud, we will expecting the data of CPU utilization, memory utilization, and storage utilization, and network interface card link utilization. So traffic transmitted out and traffic transmitted in. So these are the two types of data that we will be expecting. Based on that, we can train different type of machine learning model, and this data will be time series. So I will recommend to use like LSTM or RNN models to train such to train the model on such a data.
Okay, thank you. Good, thank you.
Any more questions? Actually, Tala is my PhD candidate student. So with this plan, we will deploy the systems into the team. Then I hope we can make a meaningful accomplishment. And based on this work, I think we can contribute to this working group more. Yeah. Okay, then we can go to the second speakers.
Thank you.
The second speaker is Shengjin Zhang, Professor Shengjin Zhang from Nankai University.
Hi, Professor. Can you see my screen?
Yeah, sure.
Okay, I will start to show my screen.
Can you start?
Yeah. Wait a minute. Hello, everyone. I'm Shengjin Zhang from Nankai University. Today, I'm going to talk about our previous works on failure detection, diagnosis, and prediction for large-scale cloud services. We all know that the goal of IT operations is to reduce time to repair and increase time between failure. And for example, after a failure occurs, the first thing to do is to do the proactive failure detection and to determine whether a failure occurs. And after that, we will try to diagnose the failure and find the root cause of the failure. And after that, we will try to conduct failure recovery and to repair the failure as soon as possible. And all the three steps, the failure detection, failure diagnosis, and failure recovery constitute the time to repair. And our goal is to reduce the time to repair. And after that, after the failure is fixed, we will try to conduct a root cause analysis and find the real root cause of the failure, and to guarantee that the similar or the same failure will never occur again. And concurrently, we will conduct the failure prediction and predict whether there will be a failure in the near future. And the time of root cause analysis and the failure prediction constitute the time between failure. And our next goal is to reduce to increase the time between failure. When we try to reduce TTR and increase TBF, we will suffer from several challenges. The first challenge is the complex edge networks. For example, when an iPhone try to access to the internet, it will go through so many network devices, and any network device failure will cause a failed access or delayed access. And when we try to localize which network device failure is responsible for the failed or delayed internet access, the manual way is error-prone and labor-intensive. Is a large-scale complex software module dependencies. And for example, as the figure shows, in modern software services, there are many software modules, and the correlation between different software modules are very complex. The third challenge is involving software technologies. It involves frequent software changes. As we all know, the software technology has evolved from IaaS to SaaS. In addition, the new software technologies such as DevOps, the native cloud computing, and the microservice architecture has also been introduced. And when the new software technology is introduced, the experience of operators is no longer fit for the new software architecture and the new software technology. And they have to learn the new experience for the new architecture and the new software technology. The fourth challenge is the complex and evolving data center networks. And as the new network technology, such as SDN and AFV, are introduced to the data center, and the data center has deployed the new technologies. In addition, the architecture of data center networks are continuously evolving. For example, as the SIGCOMM paper reports that for the era in the past 10 years, they will introduce major revisions every 6 months. And similarly, when the new network technology is introduced, or the architecture of data center network is introduced, the experience of operators will no longer fit for the new technology or the new have to learn new experience. To overcome the four challenges, we have designed a research framework to conduct failure prediction before failure, and failure diagnosis during failure, and root cause analysis after failure. And our core idea is to use machine learning to learn the patterns of monitoring data, like the traces, the logs, and the KPIs, and we conduct anomaly detection on the monitoring data. And in this way, we can transform the dynamic, complex, and heterogeneous data to the unified, universal, and structured data. And the generated alarms can be used to the failure prediction, failure diagnosis, and root cause analysis. First, I will introduce our work on trace anomaly detection. Use the background of trace anomaly detection. As we all know that many microservices have to work together to process a user's request, like the several microservices. And the remote procedure called the RPC framework has recorded the ID of each trace and the time when the microservice send the request and when the microservice receives the request and the call path of each trace. Usually there are two types of trace anomalies. The first is called the call path anomaly, like a call interruption, and the second is response time anomaly, like a too long response time. And in this work, we try to detect both the two types of trace anomalies simultaneously. To achieve this goal, we have designed a trace anomaly detection framework, which includes offline training and online detection. In the offline training procedure, we use the trace collected from a functioning system as a training set. And we first construct the path vector for each historical trace. And then we design an unsupervised training model to learn the normal pattern of traces. And in the online detection procedure, when a trace is generated, we will construct the path vector for it. And then we will conduct anomaly detection by comparing it with the learned normal patterns of historical data. And because there may be new types of traces generated because of software updates, we will construct a white list between two software updates. And in this way, we can detect both two types of trace anomalies. Transform the trace data to dimensions. We designed a simple and novel path vector. The dimension of the path vector represents the trace of the module, and the value of the path vector represents the response time of the corresponding module. To evaluate the performance of our model, we conduct extensive experiments on feedback data. And the experiments show that our model outperforms other baseline approaches. Next, I will introduce our previous work on log anomaly detection. I will introduce the background of log anomaly detection. Usually logs are one of the most valuable data for anomaly detection. On the one hand, they are very diverse because they record a vast range of runtime information. The second is that they are very general because every service and device generates the logs. And this table shows the structure of logs. And among the many fields, the detailed message field is the most important because they reveal what happens to the devices or the services. To achieve anomaly detection, we designed a framework including offline training and online detection. In the offline training procedure, we first extract templates from historical logs, and then we match historical logs to template sequences. And at the same time, we generate word vectors with word embedding. And then we construct template vectors. By combining template vectors and template sequences, we can obtain vector sequences. And then we import the vector sequences to the LSTM model to learn the normal pattern of historical logs. And after new real-time logs are generated, we will match them to templates and generate the template sequence. And then we will obtain vector sequence. And then we will compare the similarity between the vector sequences and the normal patterns of historical logos and determine whether it is normal or abnormal. And when a new type of logs are generated, it cannot match to any existing template. We will generate a temporary templates. And then we will construct the template vectors. And then we will match it to one of existing vectors. In this way, we can address the challenge imposed by new types of logs. Next, I will introduce the core ideas of a log anomaly. I will observe that some existing templates have similar semantics. And in addition, some logs contain antonyms that look similar but have updated semantics. Therefore, we design a normal framework template to work. It takes antonyms and synonyms into consideration. And in this way, we can convert log templates to soft representations. We have verified the performance of our model on the real-world data collected from Huawei, and we have demonstrated that our model can accurately generate alarms with no false alarms. Next, I will introduce our work on KPI anomaly detection. First, let me introduce the background of KPI anomaly detection. Usually, a device have several or dozens of KPIs to monitor, and like a CPU load and disk write or memory utilization. And every KPI is very important to know the status of each device. And however, conduct a KPI anomaly detection for each KPI is not efficient. And therefore, we treat all the KPIs as a whole and transform the problem as a multivariate time series anomaly detection problem. Here is the framework of our KPI anomaly detection. We first can construct multivariate time series data from the raw KPI monitoring data. And then we conduct data pre-processing, and then we train a deep learning model to learn the normal patterns of a multivariate time series. And then in the online detection model, when the new monitoring data comes, we will conduct anomaly detection based on the learned model and generate an anomaly score. And then we will determine whether it is anomalous by the threshold learned in the offline training procedure. And then we will conduct anomaly interpretation. The core idea of our framework is very simple. We use a variation autoencoder framework to encode the raw data to a hidden layer. And then we use a decoder to obtain the reconstructed xt prime. And we compare xt and xt prime to determine whether it is anomalous. It is based on the core idea that the Z represents the normal pattern of KPIs, and therefore xt prime also represents the normal patterns of KPIs. verified our the performance on the testing data. It shows that our model outperforms baseline measures. Next, I will introduce our work on failure prediction. At first, we construct failure graphs for failure prediction, diagnosis, and root cause analysis. Specifically, we process CMDB and configuration data to obtain system topology. And then we manage the relationships among alarms by active learning and obtain the alarm relationship set. By integrate the system topology and alarm relationship set, we can get the failure graph. With historical alarms and historical failure, we can constitute the training set. And by combining the failure graph, we can extract the features for failures and alarms. And then we can train a failure prediction model, which is a classifier. And when the online alarms are generated, we can predict whether there will be a failure in the near future based on the failure prediction model. We have verified the performance of our model on real-world data of Baidu. We have 3 types of switches and near 10,000 switches with 2-year period of data. And we have demonstrated that our model achieves relatively low false positive rate with high APAN score. Next, I will introduce our work on failure diagnosis. The input of our failure diagnosis model is the failure graph and the alarms. And we have designed a novel cause-oriented random walk framework to rank root causes. And then we can get the top N root cause list. To evaluate the performance of our model, we have conducted extensive experiments based on 86 online failure tickets with more than 400 microservices. And the evaluation results show that our model achieves relatively high accuracy and it outperforms the baseline measures. Next, I will introduce our work on root cause analysis. This figure shows the framework of our model. Our model have 2 components, which is offline analysis and explanation, and online root cause diagnosis and update. In the offline procedure, we first conduct anomaly extraction to extract the features of the anomalies. And then we conduct dependency cleansing to filter out the wrong correlations between alarms. Then we design a novel cluster methods to cluster alarms. And then we use the Bayesian case model illustration to find the most representative alarms for each cluster. And then in the online root cause diagnosis and update procedure, we also first conduct anomaly extraction to extract the features of the anomalies. And then we conduct dependency cleansing to find to filter out the wrong correlations of alarms. And then we conduct a cluster assignment to assign the alarms to the right clusters. And in this way, we can get the root cause of the incoming failure and alarms. We have demonstrated the performance of our model on real-world data collected from Alibaba. and we can find that the instance CPU intensive workload and the host I/O bottleneck are the main root causes of the failures, and our model's accuracy is better than baseline methods. In conclusion, we have designed a research framework to conduct a failure prediction, failure diagnosis, and root cause analysis, which is based on data mining on multimodal data like traces, logs, and KPIs. We first conduct anomaly detection to transform the dynamic, complex, and heterogeneous data to the unified, universal, and structured data. And in this way, we can generate alarms and which can be used for the subsequent tasks. Thank you.
Professor, your mic is mute.
Thank you for your presentation. During your presentation, I was very curious about whether your data is publicly available or not. You have used very various data from Alibaba or Baidu or some other places site. Then is it available?
Yeah, that's a good question. And some of the data set has been publicly available, and some of them cannot be issued to the public because the company's policy. Yeah, and part of the papers have released the data set.
Okay. Any question?
Yes, actually, I have one question. You are detecting the anomaly from the dataset, and you are comparing it with the threshold value. So what kind of threshold value you have considered for like utilization metrics? For example, CPU threshold can be like a dynamic thing. It depends upon the type of service or different activities. So the usage can also be dependent upon the type of service that the compute node is hosting. So what kind of thresholding technique you are using?
Okay, that's a very good question. And actually, we conduct anomaly detection based on not the threshold, but the normal shapes of the previous historical data of the matrix. And for example, when we try to determine whether the CPU utilization is normal, we compare the pattern of the detected movement to the normal patterns of historical patterns. Here, the pattern means the shape rather than the absolute values. And in this case, we can we can avoid the bias of just applying the threshold.
Yes, actually, you have explained the threshold in your methodology slide, so that's why I was curious.
Okay, you mean this slides? Yeah, we are applying a deep learning model called the variational autoencoder to capture the normal patterns of historical data. And then we compare the raw data and the reconstructed data, which captures the normal patterns. And if they are similar, we can determine that the raw data is normal. And if they are very different, we can determine that the raw data is anomalous.
So what kind of windowing approach you have used for a pattern? For example, a 10-minute window, or what kind of approach you have used for a pattern? So pattern should be like 1 hour pattern or 1 minute pattern. So
Yeah, we use a sliding window technique to capture the pattern of data. Actually, it's a time series which contains many data points. For example, have 2 hours of data or 1 day of data.
Thank you very much.
You're welcome.
Thank you very much. If you have any more question, please contact him personally. Thank you for your presentation, Professor Chang.
Okay, thank you. Thank you.
Then we can go to the third presentation. Third presentation is from Mr. Do Ho Young from Code J.
Hello, can you hear me?
No, actually, I'm sorry. Your presentation is the first presentation. This time, Mr. Do Ho Young should present first. I'm sorry about that.
Okay, never mind. Okay, sorry.
Can you see my presentation?
Yeah.
Okay. Start. The title of my presentation is a study of the proof test of autonomous network for Korean IP backbone network. The purpose of this study is to test AI model IP backbone network. In order to do it, we collect network data such as flow, alarm, and traffic. We apply some AI techniques to perform RCA and anomaly detection. This slide shows the overview of last meeting. Last year, AI engine for optical network was developed. It was found that the accuracy of the AI engine was 99%. In addition, self-correction and self-organizing process were developed to help network operators. A general network management system monitors the equipment status and traffic usage, and in the event of a failure or abnormal traffic, the operator takes action to fix the problem after analyzing the cause. In such a situation, the time required for recovery depends on the operator's capability. Therefore, in this study, we study an AI-based network management system that can autonomously manage by analyzing the root failure that becomes a problem when the system encounters a mass failure and determine whether there is abnormal traffic. Nowadays, network is becoming more and more complex. And furthermore, it is expected to take a long time to recover from a network failure. The scope of this study is, first, to collect IP-SDN data such as alarm, traffic, and S-flow. Second, to establish self-correction of IP network failure. Third, and to establish self-configuration according to abnormal traffic detection. Fifth, and to establish of AI-based integrated failure response process. The system architecture consists of gateway for data collection, pre-process for data pre-processing and normalization, RCA engine and AI engine for root failure analysis and abnormal traffic detection, data lake for collecting and managing large amount of raw data, and web and WAS server for GUI. The network configuration includes 6 layers such as gateway, alarm AI engine, traffic AI engine, truffle ticket, user interface, and data lake layer. Among these layers, alarm AI engine and traffic AI engine layers are key layers. Next, we establish IP network topology and developed GUI including IP-SDN switch and port configuration information, link configuration information for connecting between switches, and user information. In the data process, traffic and S-flow data is collected from IP-SDN switch. Alarm data is collected from EMS of IPSN suite. And a ping test is performed periodically. If there is no response, alarm is issued. All data is sent to data lake for storage. I would like to explain self-recovery process. AI engine is developed for self-recovery in the case of network failure. First, IPSN alarm data and ping alarm data are clustered in the time series and generated RCA object. Next, RCA object is sent to alarm AI engine. The alarm AI engine identified root failure and request ticket creation. After RCA ticket is generated, it is stored in data lake. Next, I would like to explain self-configuration process. AI engine is developed for self-configuration when detecting abnormal traffic. First, we collected IP-SDN traffic data and S-flow data and stored data lake. Then, the stored traffic data is pre-processed for learning and then put into the traffic queue. In machine learning, normal traffic patterns are learned. The traffic AI engine detected abnormal traffic by comparing it to normal traffic patterns. Abnormal traffic is put into the ticket queue and stored in the data lake. Training data is measured every 2 minutes. It is classified as abnormal when it is excessive or under traffic with low probability of occurrence. We extracted normal traffic data is a training row base. To do so, we generate periodicity, process recent 2-hour data, and standardize observation value. Several AI models are known for self-configuration: core model, time series model, linear regression model, and 1D convolution core model. The characteristic of each model is presented in the table. Please note 1D convolution core model. 3 models are simulated with traffic data collected from IP-SDN. Data 1 and data 2 are traffic data of Yonsei University and Jeju Energy Corporation, respectively from May 10th to July 20th this year. It is found that convolution 1D model provides correct result and faster computation. In the configurer, the blue line is the measured value and yellow line is the predicted value. AI compares the machine learning result with the prediction result of the existing model, and the model is automatically updated. I would like to explain failure response process. First, a ticket is issued due to a root failure and abnormal traffic. Next, an email is transmitted to the operator. Then root failure ticket initiates self-recovery process and provide the standard operating procedure. Abnormal traffic detection also initiates self-configuration process and helps the operator block the port. This slide covers the development of first response process capabilities for self-organization and self-correction. First, to handle the self-correcting process, we have developed an action profile management function. The action profile can be set by the network operator by registering, and it automatically recovers non-destructive failures such as failures to the construction. We developed equipment testing and control functions for failover and made it possible to propagate to the situation using email. Failover contents can be entered so that the system can be autonomously recover from failures that are not actually failures in the future. This slide is a web-based control UI that can monitor current transmission network and IP-SDN network. In case of root failure of abnormal traffic, an alarm ticket is generated. The equipment of the transport network and IP-SDN network was placed through the topology map. Clicking on the specific alarm ticket will not focus on the fault equipment. Alert tickets can be searched quickly through various filter functions. This slide shows the dashboard which can check the data collection status from IPSDN. This system collects real-time events from IPSDN. In order to check whether the collection status is normal, it is possible to check the usage rate over server resources, whether there is an abnormality in the collected data and the details of the collected data. This slide shows the dashboard which can check the status of the AI engine for abnormal traffic detection. This system detects abnormal traffic for each user organization line. It outputs various statistical values that can check the distribution of AI models by user organization, AI model accuracy trends, AI model driving failures, and normal operation of AI models. This is a plan for the advancement of autonomous network in 2022, securing current operation data stored during the system operation period, gather the additional requirements of the current LC operator, develop a development plan for self-organization and self-correction, establishment of development plan for self-correction process for non-disable alarms. For additional notes, non-destructive alarm are alarms generated by construction and failures that occur when the power is turned off at the user organization. During actual system operation, monitoring and operation efficiency decreases due to non-failure alarms. This slide is an advanced plan for detecting abnormal traffic to prevent network failure in advance. Advanced AI engine for analyzing traffic trends in the subscriber section or mediation section of the network. Abnormal traffic detection in the subscriber section and relay section can recognize large failures in advance and take a preemptive measures by promptly responding to failures. This slide is a plan to advance the self-correcting process. Collect alert data from IPSDN. And Alarm AI engine creates a fault ticket with the collected alarms. Abnormal Alarm AI engine created a model through learning with the failure ticket stored in the DB. When a fault ticket is generated, the abnormal Alarm AI engine determines whether it is non-blocking and performs an automatic recovery process. If it is normal failure ticket, failover is performed according to SOP. Finally, the status is automatically disseminated to operators through email. This slide is a plan to advance the self-organization process through connecting to IPSDN. When an anomalous traffic ticket occurs, the system located the ticket and sends it to IPSDN controller. If an anomalous traffic ticket is generated, failover is performed according to SOP. Finally, the status is automatically disseminated to operators through email. And this slide is a plan to advance the self-configuration process through linking with IPSDN. When an abnormal traffic ticket occurs, the relevant ticket and location information are transmitted to the IPSDN controller. The IPSDN operator will reset the optimal route after analyzing the cause. Therefore, we plan to bypass the problem section and respond to the failures. So we reviewed AI engine for RCA and anomaly detection at the current IP backbone network. Among the AI models, it is found that 1D convolution core model provides faster computation with good inference. From 2020 to 2021, we developed an AI-based route failure analysis and abnormal traffic detection engine for current transmission network and IPSDN network. In 2022, we plan to conduct research to advance the failure response process for autonomous failure response. Thank you. For the Q&A time, I'm sorry, but I'll replace the Q&A by email. Thank you.
Okay, thank you for your presentation. According to his request, or question should be emailed to him actually. Okay, thank you for presentation. Thank you. And we can go to the next, the final presentation. Speaker is Dr. Jilling Wei from National University of Defense Technology from China. Can you prepare the presentation, Dr. Wei?
Yeah. Hi, Professor. Can you hear me?
Yeah.
Yeah. Can you see the slides?
Can you start?
Okay. Yeah. Hello, everyone. It's my great honor to have this talk. And the topic of this talk is towards intelligent network application classification. And my name is Jilling Wei. I'm from National University of Defense Technology. And here is the outline of this talk. First, I will talk about the background. And according to different requirements, network traffic classification could classify them.
Dr. Wei, can you minimize the black bar in the screen?
Oh, okay. Okay. Yeah, does it look okay?
Yeah, it's okay. Thank
you. Okay, according to different requirements, network traffic classification could classify the network traffic into different categories and tag the traffic with certain neighbors. And the major process of network traffic classification is given as this figure. And the classification methods contain DPI-based method, AI-based methods, and so on. And according to different requirements, there are multiple traffic neighbors, such as protocol layer, for example, HTTPS, DNS, and so on. And service layer, such as email, chat, and the application layer, for example, WeChat, Skype, Facebook, and so on. And the application classification is to classify the network traffic at the application layer and give the source application neighbor of the traffic. So why we need to take the application classification? First, it can help the network manager to well understand the network. In addition, it can also detect the malicious or specific application so that the security can be well guaranteed. Also, by the application classification, we can also realize the specific publication discovery, and it can realize the user profile and thus system lots of upper layer services. There are two main traditional network traffic classification technologies. One of them is the port-based classification method. In other words, it classifies the traffic based on the port. For example, port 78, 79, 80. However, it only suits for identifying protocols or applications that transmit data using fixed ports. And the other main traditional method is deep packet inspection method. The other words is DPI method. In this method, it classifies traffic based on payload signatures. Actually, the DPI method is the most mature and commonly used technology in industry. For example, the top application classification software, Customers, it majorly realize the traffic classification by the DPI-based method. However, new features of network are bringing great challenges to these technologies. First is the proportion of encrypted traffic experienced a rapid growth. For example, by October of 2019, the proportion of encrypted web traffic exceeded up to 19%, and the proportion of enabled encryption in Chrome-loaded web pages reached to 95%. In addition, we also give a statistic on a large-scale mobile traffic dataset. The results show that the proportion of HTTPS traffic is close to that of HTTP traffic. So in this case, the DPI method will not effective anymore. Second, internet access shifts from desktop-driven to mobile-driven. For example, in 2019, 3.67 million apps are found at China's domestic market. Besides, the mobile internet access traffic reaches to 122 billion gigabits in 2019. In this case, some posts are used for different apps. In other words, the post-based method is also no longer applicable. In addition, there are a huge number of apps and updated frequently. So the DPI methods would be expensive to realize the traffic classification and or the application classification. Therefore, AI-based application classification method, which means the intelligent method, is proposed. An AI-based classification method do not depend on the plain text payload of traffic. It classifies the traffic based on side channel or statistical features of traffic, combined with machine learning or deep learning algorithms. And this method has attracted the most attention nowadays due to the promising performance. Therefore, it can well deal with the encrypted traffic. And here is a summarization of different classification methods. For the pod-based method, it uses the pod information as features and adopts the pod matching to obtain the final classification results. And the advantage of this method is simple, and thus it can classify the traffic fast. However, it is only applicable to protocol layer classification, such as DNS. And for the DPI-based method, it uses the plain text signatures as features and adopts the string matching to obtain the final result. And the advantages of these methods are it's also fast. In addition, it usually can achieve a high accuracy. The most important part of this method is that it is a very mature technology and thus is widely applied in industrial area. However, it cannot deal with the encrypted traffic. In addition, it usually needs high labor cost. It is used for the encrypted traffic classification scenario. For the AI-based method, it uses side channel features and adopts machine learning or deep learning algorithms to obtain the final classification result. And the advantages of this method is effective for encrypted traffic and can realize automatic learning. However, to achieve a high accuracy, it needs lots of labeled data. Therefore, it has to cost a lot of labor for the data set. In addition, the feature engineering is also a hard work. Then I will talk about the intelligent application classification. The existing intelligent methods can be divided into two categories: machine learning-based methods and deep learning-based methods. For machine learning-based methods, we need to design features first. For example, packet length, packet timing, or packet ordering, and so on. Then we need to adopt machine learning algorithms, such as random forest, Markov chains, live Bayes, to train a classifier. When we have sufficient labeled data, we usually could get an accurate classifier. The typical used features in machine learning-based methods contain packet length related features, such as packet length sequence, packet length distribution, and the statistic related features, such as the number of downlink packets or uplink packets, and the time related features, such as the inter-arrival time of packets. The typical used models contain SVM, K-nearest neighbor algorithm, random forest. And it is worth noting that random forest usually shows the best performance in machine learning-based methods. And for the deep learning-based methods, the artificial features, especially for the complicated features, are not essential. Therefore, it usually only needs a simple input, such as the original traffic or simple traffic features. In addition, it also supports extracting features automatically. Compared with machine learning methods, such models have high complexity, strong learning ability, but poor interpretability. The intelligent application classification is a research hotspot. However, it still has not been widely deployed in reality due to the following challenges. For example, these methods can usually show a good performance in closed world. However, the real network is open world. In other words, this research usually hard to apply to the real network. In addition, it usually needs lots of labeled data. Therefore, we have to cost a lot of effort to obtain the data set. In addition, the feature engineering is also hard work. At last, I will give a simple introduction of some of our work. And to help the application classification research, we developed an automatic mobile traffic collection app. It is used for Android devices without requiring root permission. Based on this app, we collect a data set for application classification. The data set is obtained by more than 200 volunteers and more than 300 apps. And the data set will be published recently. And to improve the classification performance, we propose a 3-layer classifier to identify mobile traffic and open world settings. This classifier possesses the capability of excluding unknown X traffic, even if the train set is insufficient. The first layer does a cross-grain classification to exclude unconcerned X traffic whose patterns have been. Then the second layer does a fine-grained classification to discriminate between target apps traffic. Finally, the third layer knows the patterns of each target app traffic from different perspectives and sets or strict prediction criteria to exclude those. The raw traffic data as traffic features. Therefore, the proposed model is suited for the open world cities, which contain unknown app traffic. And we collect a representative mobile traffic dataset to validate this method. This dataset contains network traffic from 116 installed on 12 mobile devices. Finally, our method outperforms the thought of the art, and the results show that the proposed classifier achieves more than 98% number of false positives. To accelerate the application classification, we also propose a method, random forest in reduced instruction set accelerate based on FPGA inspired by the reduced instruction set computer. And this model adopts a different representation of the random forest model.
Dr. Wei, you have some problem for your microphone. Actually, your voice is not clear.
Okay, let me set. How about now?
It's better.
Yeah, Professor? Does it better?
It is good. Yeah, you can go. Please keep going.
Okay. In this model, a normal hardware architecture is designed to provide storage resources and support pipeline computing. Then the instructions are mapped into the memory dynamically and are excluded in parallel. All parameters of the random forest model are transparent to the hardware until the instructions are executed in this model. Besides the apps, we also study the proxy traffic classification. In this research, we major use the behavioral statistic feature. We major use the behavioral statistic features. By observation, we found that the proxy mechanism will make a host show different behaviors according to the proxy mechanism. Several statistic features are designed to classify the proxy traffic. Based on these features, we can get a great proxy traffic classifier. In addition, we also study the VPN traffic classification. The ideas come from the observation that VPN would merge the encapsulate different flows into a new flow and transmit it. This would lead to the different in-packet features between the new flow and the normal flows. And to get more information about the app, we take the research about application action classification. and we propose an attention mechanism-based app action classification. In this method, we identify the possible action of each packet, then determine the action sequence contained in this group of flows according to the action neighbor of each packet. Okay, that's all. Thank you. And sorry about the problem of the voice.
Thank you for your presentation. Then, any questions?
Yes, Professor, I have a question. Excuse me, Dr. Wei. I just want to ask a question about the practical results of or experimentation that you may have already carried with your proposed application detection system, correct? I can imagine that you have already tried this classification on VPN traffic because I saw one slide about it. So were you able to correctly label or identify which type of network applications were consuming or transmitting different types of traffic over a VPN network? Was it successfully?
Yes, we can classify the application in the traffic due to the most of traffic is encrypted.
Exactly.
Yes, absolutely. We cannot classify most of the traffic correctly. But I think for maybe for the I think based on our statistics, maybe 40 to 30 to 40 percentages of the traffic can be classified. Yeah, based on 40, such as the machine learning methods or deep learning methods. Yeah, because we can actually we can obtain some specific features of some apps. For example, the HTTP agent and also some other features. Yeah.
Yes. Thank you very much, Doctor.
Yes, thank you for your question.
Doctor, I also have one question. Basically, you are telling this thing that we have a lab test environment in which we have collected the data and trained. So what do you think about applicability in the real world where, for example, a person is sitting in Korea and a person is sitting in China? So their application will be connecting to different servers, which means that their encrypted traffic will be different. So will this approach will be applicable globally to detect the app level traffic detection?
So your question is about the application may be from different services, right? But different servers. So you mean the traffic may be different, so it may be hard to classify it correctly. Is that right?
Yes, that's what I'm saying.
Yeah. Okay. Yes. However, also the application, the traffic of the same application may be from different servers. However, some features is still the same. For example, in some apps, it will use this third-party tools, and if we can find some features from the third-party tools, then we can find the neighbor of this application. And no matter which server is of the traffic is, the feature is not changed. That means we can still classify it correctly.
Also, one more question from my side is that For example, the application uses different type of traffic. For example, one type of traffic is that if I am using or sending a text message, this is personal use. And there are some background integration or sync traffics that are going through the application. So for the same type of application, there are different types of traffic. So is that level of classification is also considered?
Yeah. I think this is a very good question. Yeah. When we use the applications, we may take some different actions. However, just I said, actually, when we want to classify the application, we are seldom to try to decrypt the encrypted payload. Yeah, we actually using the other features. Therefore, for the application classification, the features we usually use the fixed features wouldn't change it based on the action different. No matter what action is taken or what server is from. In addition, we also take some research about the just this slide said about the application action classification. That means for this research, we wanted to classify which action is taken for the application. For example, text or video or audio. Yeah.
Thank you very much, Doctor. Thank you very much.
Yes, thank you for your question.
Professor, I have one question. Can you hear me?
Yes, I can hear you.
Okay. So can you go to the slide where you explain the acceleration of random forest?
Your voice is very small.
Can you hear me, Professor?
Still small.
Professor, can you hear me now?
Yeah.
So can you go to the slide number where you have explained the random forest acceleration?
Actually, he have already.
He already went out. I'm sorry.
Oh, no problem, Professor.
Okay. Thank you for your participation. We have completed 2 sessions, and I appreciate very much your participation and the presentation. Also, I appreciate our co-chairs collaboration. Thank you very much. I hope we can see in the next APAN workshop offline. I want to see directly in China. Thank you. Thank you very much.